Good afternoon, everyone. Oh. So this is Key Trends. I'm Alexei Melnikov, and Ron May is sitting next to me. We are your co-chairs for Key Transparency today. Let's get started. We have quite a busy agenda, so we want to leave enough time at the end for various questions and discussions. This is a non-working group forming both, so we're not going to discuss charter, but we hoping to get as much done for all the steps before that.
Okay, and as a reminder, as should be obvious, this session is being recorded. And a few housekeeping details. By now, everyone who has been here in person should know what a note wall statement is. But if for some reason you are just arriving and have never been to an IETF before, or if you're attending remotely and this is your first IETF, please read carefully this statement. Basically, what you say here is being recorded and can be used, and we must all use best practices in terms of decorum and not abusing each other. And all of the details are on this lovely slide. For those of you in the room, please wear your masks unless you briefly remove them to eat or drink something, and unless you are actively speaking at the microphone, or if we had presenters in person up here at the microphone, which we do not. And please join the on-site meeting tool from the agenda. That's the little icon you see there, the on-site tool. For those of you who are remote, please make sure that your audio and video are turned off unless you are presenting or unless you have been called for your place at the microphone.
Yeah, and both remote and on-site people use the same tool to add you to the queue so that we are fair to everybody.
All right. This is available from the list of materials on the IETF website, but the mailing list for Keytrans information is at the bottom of this slide, and the agenda and general IETF meeting information is here. And here is our proposed agenda for the next 2 hours. Would anyone like to say anything, propose a bash to this agenda? Okay, hearing no comments, we will invite Brendan to, I'm going to stop sharing this and start sharing the slides for the problem statement. Okay, Brendan, you have the control. Please take it away.
Cool, thank you. So, hello, my name is Brendan, and today we're going to talk about transparency. So, for context, right now, when people build into encrypted services, they have a ton of options for tools and libraries to securely encrypt data. Like you can choose between MLS or the Signal Protocol or OTR or OpenPGP. And all of these are really good options and they all have really good implementations. But one thing that's kind of famously missing from this ecosystem is that while you have all of these options for how to encrypt data, there's really not a good way to distribute the public keys for that encryption. If you look at almost any secure messaging app, they usually have some internal directory that stores a mapping between user identities and each user's public key. And that directory is not secured in any way. Users kind of just have to trust the server to provide them with the right public key. And what's unfortunate is that if a user doesn't have that trust for the server to behave honestly, then the encryption protocol kind of doesn't matter, because a malicious server can just give you the wrong public key. And while some apps do use like an internal certificate authority, similar to the way that public key distribution works in the web PKI, in this particular scenario, that doesn't tend to change much in terms of the trust model. You're still kind of just trusting the server to be honest. If an app is very security conscious, they'll usually at least have a screen like the one that you see on the right that allows two users to manually verify that they see the same public keys for each other. But people rarely actually do that because it's manual and it's inconvenient and you have to go talk to the person in person. I see that Richard Barnes has his hand up. Do you want to have a question?
Yeah. Hey, Brenda, just a brief clarifying question. I just want to confirm, when you say distribute long-term identity keys, it seems like the problem you're trying to address here is not merely the mechanics of delivering a key from point A to point B, but the association of a public key with an end user identity. So it seems like the problem we're trying to tackle here is assuring the fidelity of that binding. Is that the right way to understand what you mean by distribution here?
Yeah, that is the right way.
Okay, thank you.
Yeah. So the technical solution to this problem in the literature is something called key transparency. From the BOF request, key transparency is a safe, publicly auditable way to distribute cryptographically sensitive data like public keys. Functionally, it works kind of like a key value database, and you have two cryptographically assured properties about the consistency of the data in the database. The first and the most important is number one there, which is that Alice's key is seen by Alice equals Alice's key is seen by everybody else. Or another way to put that is that everyone has the same view of all of the data in the database. And that's really powerful because it lets us go from the situation we're currently in, where users manually verify that a public key belongs to a specific real life person, like named Alice, to a world where Alice's own devices can monitor her account for unexpected changes. So to think about this in terms of like a comparison, think about what happens when you log into Gmail or Facebook or any service like that. You usually will get an email saying that someone logged in as you. And if it was really you, you just ignore the email. And you can imagine if instead of that, every time you logged into one of those services, all of your friends got an email saying that someone logged in as you, that would make no sense because your friends are not prepared to do anything with that information. They don't know if that login was legitimate or not. But weirdly, that's kind of the world that we're in with end-to-end encryption right now, because if I'm someone's contact and I see that their key changes, I have no way to know if that's legitimate or not. But the power of KT is that it gives you the ability to say, you know, even if this is a malicious actor trying to access Alice's account, Alice already has a way to be aware of that. So it's not my job to figure out if this was legitimate or not. And the second property is more technical. So Alice's key today equals Alice's key yesterday plus anything new. It's kind of an append-only property. And the purpose of that is just so that Alice can go offline or like go on vacation for a week. And when she comes back, she can check that nothing nefarious happened while she was gone. So what's interesting is that, hello.
Yeah, I just wanted to interject that this is a way of solving the problem, but the transparency part is the salient part of this particular approach. Of course there are authority-based approaches, but this is the transparency, providing the visibility into what has happened, part of identity management, as it were.
Yeah, it's a slightly different approach. So instead of having an authority assert a binding that you trust the authority to behave correctly, this is a transparency approach where everybody can see the same data, and users are responsible for making sure their own binding is correct. But what's interesting is that the IETF already has a lot of experience standardizing transparency log type technology. So for example, you've got the SCIT working group, which focuses on supply chain integrity, or the Tigris working group, which focuses on digital credentials, or in particular, the trans working group, which published an RFC on certificate transparency. And all of these projects rely in some way on the idea of transparency, which is provided by a cryptographic append-only log. In particular, they use a Merkle tree, and a Merkle tree is just a tree where each leaf contains the hash of some data, and then every other node contains the hash of its children. So it kind of recurses up until you get to the single root node, which is a commitment to the entire tree. But one important difference between what all of those groups have previously built or are building is that those logs are fully public, and it's intentional that someone could go in and see everything that's logged and check for whatever they want to check for. KT builds on top of the core idea of an append-only log to provide two additional features. The first is that it has a search protocol where a user can request all of the entries related to some account, and the server can provide those entries, and it can also prove that it executed the search correctly. So the user knows that it actually got all of the entries they were looking for and that nothing was omitted. And importantly, they know this without having to download the entire log. The second feature is that it provides better privacy. So if you have the search protocol that lets a server prove to a client that it's actually showing the client everything that they asked for, kind of the inverse implication of that is that you don't have to show the client anything in the log that it doesn't need to see. Like the client doesn't need to see every entry or even any entry other than what it would be allowed to search for. And this actually ends up being a lot more appropriate for the use case of end-to-end encryption, because users don't want to have to download the entire log of every time anyone has ever changed their key just to find the key of the couple of users that they want to talk to. They want to be able just to search for the specific keys they want. And also for privacy reasons, a service provider probably doesn't want to provide a public log of every user they have. They'd much rather keep that on a need-to-know basis. Eric Rescorla? You have a question?
Sorry to be nitpicky, but Tigris does not involve a transparency log.
Oh, that was my impression from reading the draft, but okay, sorry.
I was in the group yesterday, so I'm pretty confident.
Okay. And Ori.
Ori Steele, Transmute. I'm one of the contributors to the SCIT work item, and I just wanted to comment on the sort of, you mentioned that a lot of these existing systems like certificate transparency, the entire log is public. And to be clear, SCIT does not sort of require the entire log to be public. The model there is each transparency service can maintain a log, and that service can choose to disclose either the entire thing in a public format or only certain parts based on an authorization policy. So the model there is not fully public, in the sense that certificate transparency has this sort of very public-facing sort of intention behind the Merkle tree proofs in the log. What the other comment is about the identity dependency within the certificate transparency and identity dependency within SCIT. Because of the need to think about digital identity associated with the log entries, a lot of them end up automatically including some form, primitive form, or related concepts to some kind of key transparency. And there are other sort of scenarios where, for example, as part of securing a software artifact in SCIT, you might secure some of the key material used to authenticate the issuer of claims about that software artifact. So I'm really excited about the work that you're doing here, and I think there is a lot of synergy between some of these other work items that you're mentioning, and agree with Ecker's comment about Tigris. Thanks.
Okay, cool. Sorry for getting that wrong, but thank you. So next slide. This all sounds great, but why are you telling me? Because despite KT being like seemingly a perfect fit for the problem of like this, for maintaining this user identity to user public key binding, and the fact that it's been around for about 10 years at this point, it's had relatively little serious adoption. And the question is, why is that? So from working on this myself and talking to lots of other people, my sense is that it's because KT tends to be very technically complicated, sort of in its own right. There's also a large amount of academic literature on KT, so the design space is fairly wide, and there's not much guidance on what the right choices in the design space are versus what is even possible. And also there's, in terms of actual implementations that exist, there aren't many, and what does exist often is missing important parts. So like maybe they implement the server side, but not the client side, or it has no documentation or no active maintainers. And just overall, the technical difficulty combined with how much work needs to be done to deploy something like this, combined with the lack of any outside help or validation, makes this something that people tend to just be very likely to give up on. Like a company might recognize that this would hypothetically be a valuable security improvement, but not able to justify the amount of engineering time it would take to actually accomplish. Daniel.
Hi, thanks for this analysis. I think this is pretty important to think through. I think it's missing one of the other pieces for why it's been difficult to get this deployed, which is a question of incentives. And I'm reminded a little bit of DNSSEC here. Apologies for that. But people often see DNSSEC as an opportunity to break their domain, because when you screw it up, it just looks bad for you and things don't work. And I think we have to ask ourselves with key transparency, what happens when you screw it up? But also what happens when it effectively does uncover that someone's key has been modified? And what are the implications? What are the reputational costs for the service that's running it? I think the service should run it. And I'd love to see reputational costs for services that don't run it and still distribute keys. But the folks who are distributing keys may see this as only a way that they can get whacked with the PR, negative PR stick, and don't see how they're going to get an improvement from it. It's just an improvement for their users, but not for the distributor themselves. So I don't mean this to be discouraging, because I actually want to see this happen, but I do think that we need to grapple with the incentives here, and that's not in your list.
Yeah, that's totally valid. Thank you.
And we're going to hold questions until the end of this presentation, just so that we're sure that Ren can get through this material, and then we'll have a robust discussion on the problem statement.
Okay, cool. So like I said, this is something that is technically difficult. You lack a lot of outside help or validation, something that people tend to just kind of give up on. So the ideal end goal here, or I guess I should say, this is a place where I think that a standard could have a really positive impact, because the goal is to reduce the barriers to deployment that I was just talking about, so that using KT is actually justifiable and not something that people just give up on. And I think that the standards process tends to target most of those issues pretty perfectly. So the process of actually building industry consensus around what KT is supposed to look like and how it should work helps zero in on the right choices in the design space that would satisfy a wide range of use cases. Whatever protocol description comes out of that would receive a decent level of scrutiny from security researchers and the general public, which would create confidence that it's actually secure. You'd have more trustworthy and complete open source implementations, because people will actually want to use it if they feel like they can trust it and they don't have to start from scratch with figuring out what to even implement in the first place. And then wider adoption leads to having better documentation somewhat naturally, because there's more people that need to understand it and they get better at explaining it. So the proposal for actually getting to that end goal of having a standard, this is what I think makes sense. We would start by trying to understand the broader state of what's been deployed and what's possible in the world of KT. And after that, we would try to align a community on a set of common achievable requirements that could be the basis for a standard. And if we can do that, then actually write the standard, which seems like the easy part. This meeting is meant to focus more on the first step by introducing KT and like what sorts of things are possible within the world of KT, and towards the end, hopefully we can start to move towards step 2 of talking about consensus. But that is all I have. And now we will take questions and comments.
Seeing no one in the queue, do we want to? Okay, Ecker?
Yeah, and I think I wanted to go back to this point DKG was making about incentives. The reason that CT is a thing is because not 2 browsers, maybe 3, decided they were going to require it, and everyone else had to follow along. And it is quite expensive to operate CT logs, and the history of CT logs involves quite a few, logs screwing up quite badly. So KT presumably has like similar problems, not exactly the same problems. So I think it would be we'll have to talk about the incentive problems of like who's going to actually operate this, who's going to make it a thing, right? And just to preview, the question I'm going to ask you later is like which substantial-sized messaging services actually want to do this? Because if the answer is like the null set, then like this is not worth doing. So.
Hi, I'm Conrad from Phoenix R&D. And while prior to this meeting, reading up a bit on the key transparency literature, I've been wondering, each approach seems to rely on both the distribution or seems to aim for both the distribution and the provision of this transparency for key material. And I was wondering why we have to combine these two. So do we really have to upload keys, or wouldn't it be enough to store commitments to key material or to other data? Say if you want to provide transparency not just for a key, but for more data like a user account. So why not just upload or store commitments to whatever you want to provide transparency on? Yeah, do you have any thoughts on this?
Yeah, I think that's totally valid, and that's something that you can do with the current draft that I'm going to present at the end of this meeting. It follows like basically the key value database abstraction. So you have a key, which is going to be a username, and then the value can be whatever you want. It can be a public key, but it can also be any kind of information about your account or whatever. Yeah.
All right, thanks.
Thank you.
We have Ori in the queue. If you don't see your name there, please use the on-site participant tool so we can add you.
Okay, I tried to use that one.
Or Steele Transmute, just regarding I guess some stuff that I've seen that's related to key transparency in the open source community. Like I mentioned before, in Skit and in Skit-like services, outside, there is a lot of people are starting to put keys in these transparency services that were designed to store artifacts of other types, because they want to be able to sort of generate receipts for offline verification, not just for the artifact, but for the issuing identity around some of those components. And so I wonder, how do we coordinate that identity problem across the different transparency ecosystems? Because all transparency ecosystems have some need to handle identity, and keys are a building block for identity. So again, I don't have a good answer there. I'm seeing hints of key transparency already showing up inside of Skit and some of the work we've been doing there, and I want to make sure that it all goes well. And yeah, there can be issues, around long-term identifiers that have keys associated with them when they interact with several different transparency-like ecosystems. So yeah, that's it.
Daniel Kahn-Gilmore. So I wanted to ask about the why are we not storing commitments instead of the content? So one thing is that when there is a mismatch, you may be interested in knowing, if you are the account holder, what the distributor has served about you, which is different than actually just knowing that they serve something different. I don't know what the semantic trade-offs are there, but that might be one thing. Second thing I wanted to observe was that putting just the commitment seems like a bit of privacy advantage, because maybe you're not putting, I don't know, details that might be more identifiable, but the real thing that the privacy concern is, I think, is with the name, with the account information, the account name, not with the content. The key, that is the key of the key value store, is the thing that we have a special privacy concern with that things like CT do not handle.
About this, we're actually right now deploying key transparency at Proton, and it is indeed as hard as you say. So building it, it has been a challenge, building the tree and building everything. We're using a very similar version to what's described in the RFC. And we would actually be interested into seeing this work to be standardized more. On the other hand, I want to say that even if you don't put a commitment, even if you put just the full string, the server can anyway hide a leaf. Like the server can anyway not reveal the information about a leaf. So whatever is going to happen with the commitment, I think it is important to remember that the server can just omit any part of the tree.
Aaron? Guilin? Guilin?
Yeah, thank you. So I'm Guilin Wang from Huawei International. I think actually certificated transparency is a very interesting topic. But my question is that in your plan, do you have any potential implementation methods? Like in my idea, maybe like a blockchain is a candidate. So do you have any other considerations for implementation?
Brendan, would you like to answer that?
So we don't currently plan to, I think, stray too far away from the problem that we're talking about right now, which is more like instant messaging focused, of attaching like usernames to public keys, which are used for instant messaging encryption.
Do you have a follow-up question, or?
I don't have, it's okay.
Conrad?
Okay, so sorry, Conrad Korburg again, Phoenix R&D. So thanks for the kind of responses and reactions to the questions regarding commitments versus key material. Just to clarify a bit where I'm coming from. So first of all, I share the privacy concerns, of course, and I agree that the identifier is more, important to protect, although I think it's somewhat orthogonal. I mean, you can have commitments and still try to protect the identifier. Where I'm coming from is, while we're also, I mean, at the IETF with the MIMI working group trying to standardize around identifiers and authentication, who knows where that goes, but kind of thinking separately from that, it would be great to have some sort of flexibility, because there's a lot of movement in the instant messaging space right now, and kind of fixing a certain format or whatever we put into the actual tree or transparency structure might be a bad idea, and just focusing on commitments would give us a lot more flexibility. So that was kind of where I'm coming from. Thanks.
Antonio.
I'm going to present later, but I just wanted to answer. Someone asked about industry interest in building key transparency, and Zoom is public. Zoom published a white paper a couple of years ago saying that we were going to build key transparency, and that effort is ongoing, and I'm here. So there is some interest on top of on top of Proton.
Do a poll.
Yeah, shall we?
Yeah. What do you formulate? Okay. So please excuse us. We're going to try to do a bit of a take the temperature of the room here. How do we want to figure out how people feel about the problem statement in general, and not necessarily the specifics of whether this is a commitment or the actual content. And then we can get more specific with our questions shortly thereafter. So, does the problem statement accurately express the sense of the problem?
How about we'll start? Is the problem statement well specified? Well, first.
Okay. Go ahead and say that.
Okay, so first question is the problem statement was specified so far?
So if you have not used the show of hands tool, in the same interface where you would add yourself to the queue, you would see this this question, and you can say raise hand for yes, the problem statement is well specified, or by raising hand, or no, do not raise hand. You don't think the problem statement is well specified. Okay, we'll give this 30 more seconds here.
That's pretty good.
Okay, so for the record, that's 41 people who said yes, and 42 who said yes, and 1 who said no. 43 who said yes. And with that. Okay, next question. Do we want to go into the level of detail about commitments, not commitments? We're going to wait.
No,
Let's do this later.
This is too detailed.
Do we want to? Do we want to?
Do you want to? Is the problem what? Do you think the problem is well specified?
Chairs, while you guys are working this out, it might be a good chance to give folks who are in the minority on that last one a chance to say why they disagreed.
Okay, there was one person who did not raise hand. If they want to identify themselves and make a comment, the floor is yours for a moment. Okay, Melinda Shore said, I think I was the only one in the minority. I'm not clear on whether they want proofs of inclusion or an actual distribution mechanism. And this is, let's say, this is a question that we would like to answer later in this BOF.
Yep.
Okay. At this point, I think we're probably going to proceed with the presentations unless anyone has a burning issue that they would like to discuss.
And the plan is we'll run through 3 presentations, only clarifying questions during them, and then all discussion at the end of all 3 presentations. So basically, we did a quick checkpoint to make sure that people understood what was discussed so far, and we will do another bigger checkpoint after the next 3 presentations. All right?
And one more thing about this is that while you're watching the presentations, please watch them with an eye towards this problem statement. Does your answer change based on seeing these presentations? Okay, Jocelyn, the floor is yours.
Thank you. Hi, everyone. Today I'm going to be talking about Parakeet, which stands for Practical Key Transparency for End-to-End Encrypted Messaging. And this is joint work with Lev Lombardo, who are both at Mistin Labs, Esha Ghosh, who will be presenting after me, who's at MSR, Arjan Ostuk, and Kevin Louis, Sean Lawler, all of them at Meta. So just to recap the problem, end-to-end encrypted messaging, Alice and Bob want to message each other through some encrypted messaging service. And this encrypted messaging service also holds a database of their phone numbers mapping to their public keys, for example. And in order to be able to send messages, they need to retrieve each other's public keys from the server. So Alice and Bob can look up each other on the server. Let's say they just use usernames now. But the server cannot is not bound to return the correct public keys. In fact, it can return something malicious and mount a meddler in the middle attack. And what's worse, it can do this undetected. So the solution and also the setting that we're talking about is there's an identity provider who holds a dictionary with the username public key pair such that new users can join the system. And once users have joined, they basically own their usernames and can update these public keys. They want privacy, so they want the server to restrict queries to their username. So, for example, if they blocked someone, they shouldn't be able to query this user or learn really anything about the metadata of this user. And importantly, the identity provider could cheat. So if this, and what does this mean? If the same username is queried at the same time, the actual value return could diverge in the plain setting. So this is what we're trying to address. So again, threat model, identity provider holds a dictionary, may cheat by showing diverging views. And ideally, we want to prevent this altogether. But this ends up leading to assumptions on the clients, such as having the client store secrets. But we all know how notoriously bad clients can be at storing secrets, so this is undesirable. So instead, we go with non-equivocation as our security guarantee that we're targeting, meaning the server cannot show different keys to different clients without getting caught. So at any given time, if Alice thinks her key is PK Alice, the server cannot get away with telling Bob her key is PK bad. So this slide is a little bit dense, so bear with me. Let's just talk about the parties involved. There's an identity provider who's trusted for privacy and authentication, holds this database. This is the case even in current regular messaging systems where the server holds a database, is trusted for dealing with blocked lists and so on, as well as authenticating users. For example, if you want to join WhatsApp, you have to use your phone number. But you want to eliminate trust in the server for serving these public keys correctly. And the updates on the server are basically bashed and take effect in discrete time steps that we call epochs. There's users who may update their public keys. Once they've joined the system, they may look up each other's public keys if they're permitted. They can check their own keys history up until the present epoch. And what they want is no changes to their keys without their finding out, and that their friends should receive matching keys for them. Finally, there's auditors, who are parties that are literally there to share some of the computational burden of the users. And they basically just check global predicates about whatever changes the server is making. So, for example, it could check that the server isn't destroying any records. And this could be users or smart contracts even, or designated machines, or some sort of secure computing hardware. And because this can be anybody, what we want is that they should not learn data about particular users by doing these global checks. So with that model in mind, even with that simple model, we can come up with a few components. So basically what we want is a mechanism for committing to a mutating state on the server, a mechanism to allow users to monitor their own keys, and some source of ground truth that is a way to share a small commitment. And in particular, for our system, what we wanted was to be able to support billions of users, billions with a B. And this would include, for a global scale system, users in all kinds of places with bandwidth constrained or battery constrained or computationally constrained devices. Okay, so again, TLDR, there's an identity provider, holds a table mapping usernames to public keys. We need a way to commit to this changing table and a way to serve commitments as they get changed, basically, over time. So the problem, basically, the way that we model it breaks down into commitment and verification for a mutating database problem and a disseminating small commitments problem. So let's talk about this first part, commitment and verification for a small mutating database. So yeah, there's a database. Sorry, committing a mutating, potentially large mutating database. So there's a database, you're committing to this. So here's the first two interesting problems that showed up, and there's several that showed up that I can refer you to our paper for. But basically, the first problem is state machine replication and storage layer separation. Basically, in academic work, this was mostly abstracted away, and experiments just use single machines to run their tests. But the problem is you can't just load entire large data structures into memory and operate on them. At some point, the compute cost is just going to be too much, and you also need state machine replication. You can't just have one server holding all your data, because that might go down, right? So basically, we introduced a flexible storage layer API that is modular and plugs into existing database solutions, which, by the way, I think this might be an interesting topic for having some sort of standard interface introduced. Then there's the data structure for actually committing to these states, which I think Brendan referred to this in talking about the Merkle tree. And we basically wanted to talk about use Merkle tree based data structures, because those are constructed with hash functions, so post quantum and also easily standardizable / already standardized. Turns out previous work in the tens of millions type of category seemed fine, but then when you start to scale to the scale that we wanted, even over 5 years, you'll be at more than 100 terabytes of storage. So this is a storage cost blow up. So we basically replaced this underlying data structure, got orders of magnitude better. As you can see in this slide, basically the work that is most comparable in privacy properties to us is a work called Seamless, which was if you had 10 million updates a day, which is reasonable to assume for something like the scale of WhatsApp messaging, would end up at more than 110 terabytes over 5 years, versus our work, which is barely 5. So with that, I want to mention the last problem that I have time to discuss, which is users checking their own keys. And previous work basically talked about this using either zero knowledge proofs, having the user be always online or do the equivalent amount of work, consume the equivalent amount of bandwidth, or something called append-only data structure. So basically nothing ever gets deleted. So let's just go through this one by one. Zero knowledge proofs, these are impractical for the server to do at scale. The client doing linear work, so basically being always online, is impractical for clients, especially the kinds of clients we want to support. And append-only data structures lead to ever-growing storage costs, which, yeah, I guess try convincing somebody in a corporation to let you implement something that has no way of reducing storage costs. So we basically found a middle ground, which we call secure compaction, which basically doesn't require users to be always online, but also doesn't totally require append-only data structures. Okay, so that is all I have time to talk about on the commitment and verification for the mutating database side. I do want to talk a little bit about the dissemination of small commitments. So this design space is also interesting.
You've got
Sorry.
2 minutes.
Okay, so this is basically the problem of taking this commitment and serving it to users as it gets updated. Thanks, by the way. So one option is to use Gossip, which is basically users have some out-of-band communication mechanism which they message these commitments through. Essentially, the problem with this is it can be too slow, lead to partitions, and all guarantees are basically retroactive, so damage may be done by the time you see any notification. Another option is blockchain, so using a smart contract, for example, but these are, one, too heavy on the client, two, you might even just flood the blockchain. So what if we just like had a custom version of something like blockchain? That ends up needing consensus, which is also inefficient, complex to implement and analyze. I had a montage of papers to show you, which the animation isn't showing up just yet right now, but basically consensus not good. We basically opted for something called consensus less strong consistency, which you can basically say, let's say there's some independent witnesses that can sign these updates, and then you can use existing server infrastructure for compiling all these signatures and serving them to clients and responding to requests and stuff. The observation here is the insight here is basically the server is already trusted for compiling the updates and updating the underlying database. So why not just use that for other things? And I guess here's a little schematic, but let's not go over that. The point I want to make is that doing this is basically as good as Byzantine fault tolerant consensus protocols, except you trade liveness for getting something much faster. And it can be used in addition to other mechanisms, easier to implement, uses existing server infrastructure, users get certified commitments every time they query. And it's also actually very good. It's very fast. The latency is under 5 seconds, even if you have a ridiculously high number of updates per second, which you don't expect. And yep. So I guess
I made an
TLDR.
arithmetic error. You have 3 more minutes.
Oh,
You can just slow down just a little bit.
this is actually the last slide. So I guess
Thank you.
our goal was to scale to billions of users. This had two components: scaling the underlying cryptographic primitive using easy to standardize cryptographic tools, and scaling distribution of small commitments for all kinds of users in all kinds of places. And we basically explored and addressed both problems while ensuring privacy. And there's also other things that show up, other details that show up when you start considering this type of setting. And for that, I defer to our paper. So thank you for coming to this talk, and thanks to my collaborators. All of our code is open source, and the links are in this paper.
And Jocelyn, do you want to comment on the problem statement briefly?
Yeah, I guess, I mean, this is basically what I covered in the first couple of slides, right? So encrypted messaging service, there's a database on this service. Users basically want to make sure that they have consistent views of this, and be able to detect if they are getting inconsistent views at some point.
So for the less, the folks with less domain knowledge that may be attending, this is a good match for the problem statement, in your opinion?
Yeah. Yep.
All right, thank you.
Thank you.
Antonio, I'm passing to you.
All right. Hi everyone. Thanks to Brandon and to the chairs for the invitation. Since I'm new around here, a couple words about myself. I finished my PhD in cryptography in 2019 from Cornell, and then I joined Keybase as a cryptography engineer. In May of 2020, Keybase was acquired by Zoom, and that's how I got to my current role. So in this presentation, I want to give you an overview of two different key transparency systems. One is the one that is been in production at Keybase since 2014, and the other one is the one that Zoom is planning to deploy. And in addition to looking at the details of these key transparency systems, we will look at how the concept of a user identity is different between Keybase and Zoom, and how that informs the characteristics of the transparency systems. And then we're gonna compare and contrast them, and I'll comment on the statement. A couple of legal disclaimers. I'm gonna omit some important details. I won't always be 100% accurate for the sake of brevity. This is for informational purposes only. You can read the rest of the statement. Okay, let's get into it. Keybase. Keybase starts as with the mission of giving people a way to map their online identity to their public keys in a way that is publicly auditable and as secure as possible. So the idea is people know you through GitHub, Twitter, Facebook, whatever, and they want to know what your public keys are. And Keybase is trying to build a publicly auditable directory that allows everybody to go check the public keys connected to the identities of the people that you know online. And we were trying to do this in a very simple and easy to use way. So users don't even need to actually think in terms of public keys. They just think in terms of what devices they have, and each device has its own key. And on top of this directory, we have built a lot of very interesting applications such as chat, cloud storage, file sharing, etc., etc. And Keybase is the only key transparency system deployed in production to the best of my knowledge, and it's been running for quite a while, since 2014. So what does an identity at Keybase look like? So we have an immutable username that is used actually as a key in this directory, and this username is connected to a mutable set of devices and keys, so people can add devices, remove devices, and so on. And then also as part of this identity, we have what we call the social proofs. So in this case, Max, the former CEO of Keybase, is declaring publicly that he is user Max tag on Twitter, and he can also automatically post a tweet containing a hash of his identity on Keybase. So when Keybase clients show Max's profile, they actually go to Twitter and check that this statement, that the hash matches what the server is serving. And on top of that, we have the ability for users to follow each other and so sign over each other's identity, which builds some sort of web of trust system. And Keybase identities are public, so you can look up the identity of any Keybase user just by going on the website. The way that cryptographically we store these user identities is as a list, as an append-only list of statements that describe the changes of this identity over time. So in this case, maybe Alice starts using Keybase. She has her first device, which has its own public key, and she posts this statement, which is signed by the public key of her first device. When she wants to add a new device, and the statement that says, here is my second device, is both going to have a pointer to the, a hash reference to the previous statement, and it's going to be signed by both their new device and their old device. So the way this works is that in the app, you actually need an existing device in order to authorize a new device to use the app, and you would scan a QR code or something like that. There are other kinds of statements that go in the identity, as I was saying, social proofs, and then you can also not just add, but revoke devices. And what happens here is that all of the statements then get posted in the transparency tree that we have, as I will explain later. So one problem that we started having at Keybase with this system is that since you need like new devices, an existing device in order to authorize a new device, users would like just lose all of their devices and then be upset that they can't, that they get to lose their username. Of course, we can't recover their data, but we could do something about recovering the username. So a few years later, we introduced this ability for users to reset their account, which is essentially amounts to put another statement on their chain that says, I lost all my devices, I want to start from scratch. And since this is supposed to be very rare, when this happens, like we can show to the users, to the conversation partners of these people, a very scary message with like an actual skull in there that says, oh, you know, the keys have changed. Please like confirm with them that this is legit before letting them in. In contrast, when your keys on WhatsApp change, you get a notification that says your security code has changed, and people don't really like act on that; they just ignore it. And so yeah, we require like explicit consent, and after that is given, we actually re-encrypt previous conversations for the new keys, so that users don't need to necessarily lose all of their history. This feature can also be like disabled. We have what's called lockdown mode, where these resets don't work, and also all other changes from the website are disallowed. You just need a device to be able to do anything. This is something that relies on the server. We could potentially let users add a link to this chain that says, please never ever accept reset to my account, but we haven't done that yet. The way that Keybase's Merkle tree works, it's again like a Merkle tree, so it's like this prefix tree, which essentially allows you to prove that like a value is associated with a specific label. And in our case, as each user on the system corresponds to a leaf in the tree. So the label is just a hash of the username, and the value is the hash of the seed chain. One thing that's important about our system is that, unlike, for example, in certificate transparency, the app actually blocks whenever the user is updating their keys or set of devices or whatever. So these updates need to be very fast. The Merkle tree itself is publicly auditable. We even have an HTTPS API that you can go and play with. You can look at the Merkle root. You can look at the intermediate nodes. You can do the hashes yourself, etc. We post the root either to the Stellar blockchain. Before we used to have Bitcoin, but we're trying to make sure that guarantee people that we don't change this after the fact. So that was Keybase. Now let's talk about another key transparency system, the one that we're building for Zoom. So I don't need to tell you what Zoom is. It's a communication platform. The important bits are that in May of 2020, we published this white paper where we were describing a plan to bring end-to-end encryption to our users and a notion of identity that does include like a key transparency system. And currently we use end-to-end encryption not just for meetings, but also for other stuff. The identity that we use at Zoom is different from the one that we had at Keybase. So this identity consists of two components. The first component is a set of like user identifiers, and we use two. We use a domain name to identify the account which a user is part of, such as a company or a school. And we believe that identifying the organization that someone works for is often the most important piece of a user's identity. And in this case, administrators of the account will have to select and prove ownership of this domain name before it can be used to represent the account. And then individual users within the account will be identified by their email address. And note that these identifiers, unlike in Keybase, they are mutable. So users can change email addresses, they can move between accounts, and so on and so forth. The second part of the user identity, like in Keybase, it's a list of devices, and this list can change over time. You can add and remove and so on. We also use seed chains at Zoom, but with some differences. So first, like, you know, the user seed chain is now indexed by this like user ID, which is not anymore the hash of a username, but we have a list of additional the additional identifiers that are linked in the statement. And another important difference is that when we allow users to add devices without having to have an old device available to do the addition. So in this case, the addition of the second device can just be a self-signed statement. And then the vouching, like the old devices can vouch for new devices by approving them in a secondary link that can come afterwards. Another important difference is that since these identifiers are mutable, we need to keep track of which user corresponds to which identifier and how that changes over time. So we have additional chains, one for the users and one for the identifiers. In this case, the email. And then another important feature that we have that we just launched yesterday is that's related to key transparency, even though it's not actually in scope for this draft, is that we allow like external identity providers to vouch for the identity of like members of like an account. So many businesses, delegate their authentication needs to these external identity providers such as Okta that offer this centralized service that manages access control to all of like a company's resources, and they also allow users to use like just the same set of credentials everywhere. And the idea is that we're partnering with Okta, but we hope to add more identity providers so that they can issue signed cryptographic attestations, validating that a user belongs to a specific company's account and validating that user's public key in a way that the Zoom server cannot tamper with. Now, for timing purposes, I don't think I'm going to go over this, how it works, but you can read more about it in our white paper. From the point of view of the actual transparency tree, we are using like a data structure which we analyzed in a paper which was published in AsiaCrypt last year. The main differences from what we were doing at Keybase is that instead of using a single leaf that gets updated that contains the hash of a SIG chain, we store each statement of the chain in a separate leaf in the tree. And this is because that way we leak less information about when a chain is updated. Instead of using like a simple hash to compute the position of the statement of the SIG chain link in the tree, instead of using a hash, we use a verifiable random function, which essentially is a way to add privacy to this system, because you can't just verify. You can only verify where a label is located when the server gives you a proof, but you can't compute the value yourself. And then, as some people were anticipating before, we for the value we actually use commitments, and we don't post the value directly, again for increased privacy. With respect, the disadvantage of this system now is that if Alice's like chain contains multiple statements, we need to do more than one inclusion proof in the transparency tree. So if you want to compare the two systems, at Keybase we have immutable usernames, at Zoom we have mutable identifiers. In both cases we have ways to have like to connect like the identity within the system with identities that the users hold outside of the system. At Keybase, we have a stronger stance. Adding a device requires a signature from an existing device. At Zoom, we decided to relax this a little bit, and so devices can be approved after they've been added. At Keybase, user identities are public, while at Zoom we care more about making them private and not leaking information about the SIG chains when we don't have to. And for that reason, we use like a different data structure, a different tree design, and which allows us to have like less leakage. And we pay for the additional privacy with like a slightly less efficient construction. That's all I had for you. Thank you for listening.
Okay, and Antonio, I'm going to ask you the same question
yes.
I asked Jocelyn. Yes.
Sorry, forgot to mention. Yes, I think that that the problem statement would be like a good match for what we're trying to do. I think, as I presented, like there's like sort of more stuff beyond what the problem statement is capturing that we are doing, some of which I have presented here. So I would see it as a good like I would want for what we build to be like extensible in a way that we can also do like in a way that we can like allow for these additional applications as part of the and integrations as part of the standard. Thanks.
Thank you.
Okay, Asha, you have the floor.
Thank you. Thank you for chairing this, and thank you very much to Brendan for inviting me to give this talk. So I'm also new to this, so I'll do a quick introduction. My name is Esha Ghosh. I'm from Microsoft Research, and I have graduated from Brown University I'm as a cryptographer in 2018, and I've been in Microsoft since then. And I've been working on strong privacy preserving key transparency systems since the last 5 years. So many of the proposals discussed today, I have been co-author on those works, such as Seamless and Parakeet and RCKS. And this is very exciting that there is a proposal of us coming together as a community and building key transparency specifications. So Kevin Levy from Meta, I was trying to understand what sort of security and privacy properties would make sense for a key transparency systems when we go for a standardization, and many of those things already came up in today's discussion, so that's great. So this is just an attempt to bring some discussion points to the table and see if we can go from here and agree on a set of requirements for key transparency. Okay, so this slide is a quick recap of what the problem statement of a key transparency system is. And this has already been discussed by Brendan, Jocelyn, and Antonio, so I'm not going to go into too much detail here. But the moot point here is that there is a service directory service provider who maintains a username to mapping public key directory service and gives the key out on the client's behalf. They also posts tree heads, Merkle tree heads or commitments periodically on a public bulletin board. And I'm going to talk about this in a moment too. And when a client gets a public key from this directory service, it also gets a cryptographic proof along with it, which it can verify against the publicly posted tree heads. So in the system, the service provider basically commits to this directory of username to public key mapping, this key value store, and publishes it on a public bulletin board. And the users or the clients of the system interact with the service provider in 3 ways. So the first is they can register with an account or update their public key. And the second is they can look up their contacts' public keys. For example, Bob can ask for Alice's most recent public key because he wants to connect with Alice. So server will return a proof along with it, which Bob can verify with respect to the latest tree head. And Bob's device can also monitor its own key history, which has also been alluded to in Brendan's problem statement, which is the transparency aspect of it, and it can verify that that history is maintained correctly. So the goal of this talk today is trying to understand what correctness, consistency, and privacy properties might be achievable and might be important for a key transparency systems. So before diving into that, one quick comment about the dissemination of the tree heads or commitments. So in the slide, I mentioned a public bulletin board. So that's one way of disseminating the tree heads. And the idea here is that all participants of the system, meaning all the users, should be able to see the same tree head for a given epoch. Otherwise, there's a forking attack possible. So the currently deployed or proposals for key transparency systems either work with either of these 2 assumptions. So either there is a third-party public bulletin board where these tree heads are posted, or it's assumed that there is a gossip channel between the different participants in the system so that they can compare the tree heads directly with each other. So with this, I was just trying to follow the chat, but I'll probably come back to it later. So with this in mind, we are now ready to look at some of the properties that we think might be important for key transparency systems. So the first property, I'll actually first talk about correctness. So what does it mean for a key transparency system to be correct? It's basically if the service provider is honest and a certain user, say Alice, is honest, then another user, Bob, should always receive the correct public key for Alice. So that should be the correctness, we think should be the correctness for key transparency. And then the more interesting properties are consistency and privacy. So for the consistency property, the property that we want is the following. Say Bob's latest public key is blue, but the server sent, when Alice queried for Bob's latest public key, the server sent a red key, which is a fake key. So the consistency property required in key transparency means this will be detectable, and the properties can be sort of separated in two parts depending on who and when this can be detected. So the first thing to note here is that only the owner, which is Bob, will be able to authoritatively decide if this was a fake key or not in the system. So it seems that at least two checks would need to happen for such a fake key distribution to be detectable. So one is Alice needs to ensure that the key she got for Bob is in fact committed by the server in the latest tree head. So she's seeing a stale key for Bob. And then Bob, the next time he comes online and checks his own key history, should see this fake key in that history and should be able to detect it. So based on that, we think for consistency, it might make sense to separate two different flavors of consistency properties. And also there are existing systems, key transparency, academic literature proposals out there that achieve some of this, some of them achieve strong consistency and some achieve weak consistency. So by strong consistency, we mean we are in the strongest case where Bob detects such an inconsistency the first time they come online since the distribution of the fake key, and does the monitoring of their own key history. In the weak consistency property, it's we need additional checks for that. So let's say a fake key was distributed to Alice. Bob came online after that and ran his key history check. It's this fake key detection, fake key distribution may still not be detectable. So additional checks might need to be performed by Alice or other parties in the system for this to be detectable. And in weak consistency, we say either Alice or Bob should be able to detect it. It's not necessarily that only Bob will be able to detect it. And there are existing proposals out there that sort of fall in one of these two categories. The second property that we want, it's not exactly a consistency property, but it's a property that you may need to achieve consistency, is what we call contact statefulness. So if each client has to remember the last keys and the version numbers or any other auxiliary information for its contacts, not for its own key, but for the context keys that it had fetched in the past, and if this is crucial for the client to be to achieve consistency of the system, then we say that the system is context stateful. Otherwise we say that this is context stateless. And yet another property which also came up in the discussion before is owner signing. So that gives stronger than consistency properties. So what does owner signing mean? It means whenever an owner, say Alice, changes her key change is signed by one of her existing keys. So in that case, if our whole keys are not compromised, then the server or any other malicious party will not be able to inject a key on Alice's account. But of course, she can lose all her device, which will lead to a full reset to her account. But even in this case, we can achieve a strong property, which says that if a malicious server publishes a tree head at a certain epoch, and after that a user's device was compromised, the server still should not be able to have clients who hold this tree, except any keys that the user's device did not authorize before the corruption happened. And this property is stronger and somewhat orthogonal to the consistency property I mentioned before. And then I'll talk about the privacy properties, which also came up, this discussion about commitments and what privacy can we achieve in the key transparency systems. So broadly speaking, I think key transparency systems, we can say, have you can think of aim for two kinds of privacy. So one is content hiding, which is what we were discussing earlier today in the meeting, which is it hides the public key and the usernames from the trees. So basically, instead of putting the raw username, a verifiable random function is computed on the username, and that random string is the position in the tree, in the Merkle tree. And again, instead of committing to the raw public key, a commitment is posted to the tree. But there's also a stronger privacy notion which some systems such as Seamless, Parakeet, and RCKs achieve, which is metadata hiding, which means it's not only the content itself, but also when the users are registering, when they're updating their keys, these information are also hidden from the public tree. And there is yet another stronger property which was proposed in the RCK's paper in AsiaCrypt last year, which is healing from a server state compromise. So because verifiable random function requires the server to maintain a secret key to retain this privacy, there is a possibility of that key getting compromised. So if the key gets compromised, how can the system heal from it once the server rotates the key? That is called post-compromise security, and that has been recently proposed too. Okay, so those are some of the interesting properties that might be interesting to aim for a key transparency system. And finally, one more comment I would make about the deployment modes I talked about the bulletin board and the gossip part already, but there are two other ways we can think of the deployment mode. One is the third-party management mode, and the other is third-party auditing mode. So the third-party management mode is you can sort of think of that the tree heads are disseminated through a third party, a quorum of parties, but the audits are happening preemptively. So if the audit fails, then this tree head doesn't get published, as compared to the third-party auditing mode, which is similar, but the audit can happen with a lag, which will lead to after-the-fact detection. And with that, I will conclude my talk here, and will be happy to take questions. Thank you.
All right. So I'm going to ask Esha for you again to give answer the same question that I asked Jocelyn and Antonio, which is about the problem statement. How do you feel the problem statement accurately reflects the problem? And then I have a personal question that I entered the queue for.
Okay. Yes, absolutely. So I do agree. I think the problem statement accurately reflects the problem, and I think that that's the starting point of why I started writing this slides for actually talking about the important security privacy properties when we have that problem statement.
Okay, Rowan from the floor.
Esha, how many systems did you evaluate in total? And specifically, did you evaluate Parakeet and Keybase and the Zoom proposal in your analysis?
So I evaluated more than that. So whatever existing literature is out there, I evaluated based on those. But yes, more specifically, I did evaluate Parakeet and RZKs. I haven't evaluated the exact Zoom proposal, but the RZKs paper that was in AsiaCrypt last year, I did evaluate that.
Okay, and approximately how many key transparency sort of proposal algorithms or proposals did you look at?
So that would be around 10.
Great, thank you.
Richard?
Yeah, thanks, Esha, for this presentation. I had been thinking in the last few presentations, it would be great if someone had a synthesis of all these variations. So I think this is a great great analysis, and I think will be a good starting point for further refinement in the working group. This is a comment, not a question, sorry. But I just think as we look forward to hopefully eventually chartering a working group in this area, I think this analysis that Esha has done should be a guide in that we are going to have the working group develop a single thing. And so wherever there are choices here about whether we get property A or property B, we'll need to make choices. And those would be good. To the degree we can make those choices up front in the chartering stage, that's obviously better. If there's cases where we need to figure out how hard something is and defer a choice, we should do that deliberately. But I think this is a nice framework for kind of making those decisions. So there's probably a follow-up call to figure out what the right set of properties is for the thing that's working your Google build. So, thanks, Ganesha.
Thanks, Richard.
So do we want to the discussion?
So I see a question in the chat from Daniel. Should I respond to that? It's a bit confusing. Interaction between the VRF and the user identity. How can the user know that the only key published associated with their identity is their actual key? So that is a great question, and that's why the abstraction which differs from, say, certificate transparency is here. This is an authenticated dictionary abstraction. So it's actually very important to have uniqueness. So basically, you cannot prove membership and non-membership of a certain point at the same time by the correctness of the system. So basically, on a username, if you compute a VRF and you can prove that the VRF was computed correctly, and you prove you open the commitment to that path in that tree and prove something, you cannot prove another contradictory statement there. I don't know if that answers your question, Daniel.
It sounds like you have an answer for it. I don't understand it yet, but I probably need to read more. So thank you.
Just verify that we're still on this page.
Okay, any further questions on the whole set of presentations so far? Okay, so if you want this, is it fair enough?
Yeah.
Since you're soliciting comments, I would say the overall impression I'm getting here as a newcomer to this space is that we're probably going to need to identify a subset of the overall functionality that is in systems like Parakeet and like the Zoom system that we're going to standardize. So we'll need to find a cut point between the thing we're going to standardize and which parts are in that and which are special to the things like the Zoom system or Parakeet.
Okay, so there's a poll here. We're just checking in, making sure that we think that the problem statement is still on the right track based on seeing these presentations.
So in ideal world, all the presentations should have clarified the bigger picture as opposed to getting you more confused. That's basically the high-level question we're asking.
Okay, we'll give it 30 more seconds here, but this is looking very good.
Don't jinx it.
Hmm?
Don't jinx it.
Okay, I'm going to go ahead and end this at 34-0. So thank you. And 37. Wow, great. Okay. Okay. We'll queue up Brendan's slides here.
Wait. Do we want to have the kind of, I know the kind of questions.
Yeah, let's do it. Yeah. Oh, we have somebody in the queue here.
Okay, so quick question from Maxime. Okay, disappeared. All right. Chairs are feeling slightly optimistic. So we'll ask a question about, do you think that should this work be done in IETF?
Okay. We were at 35-0. I'm going to call that strong. 36-0. I'm going to call that strong consensus.
In the room, Richard, do you have a comment?
No, I'll just express the chat, sir.
right.
So with that, we'll go to the last presentation from Brandon, where it's basically a straw man on a starting point for addressing the proposed problem.
In 2 parts. Yeah, and this presentation is sort of split into 2 parts. There are the first 2 slides, which are more general about kind of talking about the problem. And then the second half is a specific way to address that, as was addressed in Brendan's draft. Okay, you've got the floor, Brendan.
Okay, cool, thank you. So yes, this presentation is on draft Macmillan key transparency, which is the individual draft that I wrote. This is meant to be my best guess at what a standardizable middle ground protocol for key transparency would be. So please keep that in mind, that especially as I'm presenting, at least in my head, everybody is agreeing with me and nodding along. So if you don't agree with me, then that is something which is valuable to share either here or potentially on the Keytrans mailing list, because I kind of do expect this conversation to spin out. But yeah, to start by introducing the basic model that I think makes sense, what we have in mind is a protocol between a client and a server, conceptually pretty similar to a key value database, where the keys are potentially user identifiers and the values are essentially arbitrary information about a user's account. I mean, ideally there's a public key in there, but it can be any byte string that you want. Users can submit search requests to look up the value of a key or update requests to change the value of a key. And they can also do something called monitoring, which is basically a search, but it's optimized so that users can repeatedly look up their own account with the understanding that they are not actually looking up their own account. They're just trying to check that nothing has changed without their permission. And importantly, something that's not mentioned on here is a transport layer. The draft does not specify a transport layer, although it does specify a format for protocol messages so they can be encoded. But we generally assume that operations are happening within a broader application layer protocol. So we can let the application layer handle things like user authentication and rate limits and access control and all of that stuff. And we can just assume that if we send a request and we don't get a response, that the application layer blocked it, and ideally also told the user why it was blocked. You know, like maybe an application only lets users look up keys for people that they are friends with. So if a user tries to look up a key for a stranger, the service provider can just drop that KT request and tell the user like, hey, stop that. I also made a choice to try to avoid out-of-band communication unless it's really necessary. So it says that the user generally only needs direct communication with the service provider. The reason for that is because it can be pretty hard to get strong security guarantees from things like out-of-band communication. Like if you think back to the QR code scanning screen that I mentioned from my first presentation, if nobody does the QR code scanning, then you don't actually get anything from having it. Yeah, so you can have maybe the same issue from like client-to-client whisper or like gossip that works over like Wi-Fi or Bluetooth. What if you're not on the same Wi-Fi as anyone else that uses that? You can't gossip with them. So because this would be a standard, I think that you would want the security to be robust in a wide range of scenarios, and trying to kind of avoid out-of-band communication does help with that. So that's the model. The design goals that I think make sense to stick to are grouped into some different categories. The boring, non-controversial design goals are, number one, we want efficient verification processes in small state. Like this should not be something which is a drain on users' devices. Also, we want to avoid cryptographic algorithms that don't have a straightforward path to being post-quantum secure, because we don't want to have to redo all of this work in a couple of years. On the maybe interesting side, I would like new entries to be added to the log immediately. Normally in systems like this, it is typical to do batching. So a user would submit a request to change their key, and then the server waits to batch it with a bunch of other changes to the tree at the same time. This internally makes some things easier for the server, but from the user's perspective, every time they change their key, they have to wait an hour before the change takes effect, which is super annoying. It's much simpler if the user can request a change to the database and have it published immediately. That does affect the architecture of this system though, like whatever database the service provider uses needs to prioritize consistency over availability, which means that it can be harder to prevent outages because you need to come to consensus about the tree very quickly if you need to add new things to it immediately. But in my opinion, it's worth it. On the more interesting side, I think it would be really important for a standard KT protocol to be able to operate securely without a third party. Most KT constructions in the literature assume that there is like a big powerful third party out there that can download the entire log and double check everything to assure users that the service operator is behaving honestly. But from talking to people who would be actual candidates to deploy KT in production, I've heard a lot of reluctance to actually create a third-party dependency in something which is pretty core to their service because this is interfacing with their user management system. So there's reasonable worries that if you stick a third party in this, that the third party could go down and cause an outage for you, or you might have to pay the third party and you don't want to do that, or it's just overall too much of a headache to manage this new relationship. So of course, on the other hand, the reason that there is so much academic literature assuming a trusted third party is because having a trusted third party is really compelling in theory because you can get a lot of efficiency and security benefits. So overall, people tend to fall on one side or another of this trade-off where either they're willing to support a third-party auditor in exchange for those security and efficiency benefits for their users, or they don't want to deal with a third party and they are more so fine with using a protocol that is maybe less efficient or has some rougher edges security-wise. And I will talk in a few slides about how I think we can manage that trade-off. But something else that I wanted to say first is that this draft doesn't cover or doesn't consider metadata privacy, which is the second part of the interesting design goals. Well, design non-goals because it's not considered. So because of that, it can potentially leak the approximate number of users in the system, and it can also leak how often a specific user updates their key. So it doesn't leak like the content of the update. Nobody that's not allowed to see an update will be able to see it, but they will know that the update happened. So that's what you were leaking there. My sense is that maybe we can live without the extra complexity of metadata privacy, but that's not a super opinionated take. That's just, I didn't consider it in this draft genuinely. But yeah, so those are the design goals.
Brendan, there's some
Yeah.
robust discussion going on in the chat. Would you like to have discussion as we go here, or would you like to folks to hold things for the end?
So
That's
we
great. We actually just got to intermission because I'm aware that this is already a lot of controversial content, and I'm going to now give you the opportunity to yell at me about it.
And so Brendan, if you can go back to the previous slide during the discussion, I think that'd be useful for everybody to have that as a reference. Thank you. All right, don't all jump up at once, folks.
Yeah, I mean, everyone's talking a big game in the chat. Nobody wants to come on mic. So I put it in the chat, like I think this secure without third-party auditing is interesting in the sense of being impossible. Like I don't think there's really any plausible system where you don't have to have some sort of third party checking that there's no equivocation by a log. Now that said, I think that checking can be fairly lightweight. If you look at CT, checking consistency proofs to verify there's a single linear history is a very cheap operations, and I think we could do something similar here. But I think that you have to have some external source of truth other than the log in order to prevent the log from equivocating. So I'm comfortable accepting that constraint.
You're comfortable accepting can be secure without third-party auditing?
No, I'm comfortable accepting the constraint that there has to be a third-party auditor.
Ah, gotcha.
I mean, absent some demonstration that there's some magic that causes that not to be necessary, which, as far as I'm not aware of, as far as I know, there's not such a thing.
Raphael?
Yeah, hi, Raphael Robert from Phoenix R&D. Yeah, thank you for putting that together. One thing that I suddenly remembered.
A little closer to the mic, please.
Okay, sorry. Yeah, thank you for putting it together. One thing that I remembered when I saw that on the slide now is that a really long time ago, when I was still working at Wire, there was some discussion between Wire and Google when key transparency was sort of new. And so regarding the metadata privacy, the person from Google back then told me that there would be a way to sort of prevent that or prevent leaking the exact number of users Wire would have had by creating like fake entries essentially. So that you could only infer a theoretical maximum number. So yeah, just putting that out there. I don't remember all of the details, but that might still be relevant. And another aspect that probably doesn't need to be part of any future standardization, but that would be good to talk about is the gossiping that was mentioned earlier. Because in terms of security, that makes a huge difference if such a mechanism exists. Of course, it's very specific to application design choices, I guess. It depends on the protocol you use. But since we have MLS now as another proposed IETF standard, there's an interesting dynamic between the guarantees that MLS already give you, because there's this guarantee on who's in a group already. And you can, if you combine that between different groups user sees, for free you already get pretty good guarantees. So this is kind of the missing piece of the puzzle in a way, so that you can interconnect groups you're not really part of. So yeah, I would just want to put that out there, that it might be interesting to discuss that, what kind of security guarantees you really get in the end when you use this system in a specific messenger.
This is Daniel Gilmore. So I wanted to highlight, I think maybe people are talking past each other about third-party auditing. There's two ways to think about this, and I'm not sure which way each person was talking about it. In some systems, they're designed with a specific designated trusted third party who ensures the security. And other systems are designed where anyone can act as the auditor, meaning they're a third party, they're not the key holder, they're not the distributor, but anyone can step in and identify when there are problems. And I think what Richard was saying was he doesn't believe it's possible to do this without there being somebody outside, but I'm not sure whether, Brendan, your slides here are talking about designing a system with a designated trusted third party that everyone has to depend on. So I just wanted to highlight that there's some confusion about how we talk about it. I do think that it's also worth us thinking about how this system interacts with other forms of identity verification. I don't know whether we need to think about it specifically here, but like if this existed, would the peer-to-peer identity verification go away? Would there be no more key verification between peers via QR codes or Bluetooth or whatever? And if it doesn't go away, how would a system like this, or a failure in a system like this, or a failure in the other form interact with each other? Like what if they're going to disagree about what's the right key? What is the actual consequence? So I just think we need to think a little bit about what happens when any of these systems flag a failure.
If I could just add one thing to Daniel's comment, we already have this problem where we have, to the extent that if you have manual verification and an authority-based verification, that those can disagree already. So we've already kind of gone through some of the user interface cases for that in a few systems.
Conrad again from Phoenix R&D. So while we're talking about architectural choices in terms of auditing, I was wondering if it might be worth to consider, since I'm speculating here, but MIMI might, the MIMI working group might end up in a space where we have a federation of messaging providers, in a place where we don't have one big deployment like certificate transparency, but instead we have maybe multiple key transparency deployments where individual messaging providers or identity providers can host their own instances, and then we can have a big instance that connects them by, again, sorry to return with the commitment stuff, but uploading the tree hashes and kind of have another tree hierarchy on top of everything. And, yeah, so wondering how people feel about that.
Okay, unless anyone has any more burning, urgent questions, we'll let Brendan continue his presentation with the sort of details of his proposal. And we'll leave some time at the end for us to ask the big questions.
Okay, cool. Thank you for that. That was good feedback, by the way. So as I was talking about earlier, there is a trade-off between efficiency involving a third-party NKT and the kind of operational simplicity of having a single-party deployment. The way that I think that we can manage this is with something called deployment nodes in the draft. And the core idea here is you can take a KT construction from the literature that works for single-party deployments and then define a way that you can optimize it in the event that you have a trusted third party. So this is a way that kind of everyone can be happy. You can either use the base construction, which works for single parties, or if you have a third party, you can get the optimization benefits as well. The actual construction that the draft is based on is from a paper called Merkle Squared, which was just published in 2021, I believe. And I chose it because it was one of only 2 constructions I was able to find that actually supports single party. And this is the one that was more formally analyzed. But the good news is that it is pretty amenable to this idea because you can kind of cleanly strip away different mechanisms from inside of Merkle Squared if the security that that mechanism provides isn't necessary in some use case. And the deployment modes that are described in the draft are first contact monitoring, which is the single party one. And then you have third party auditing and third party management, which both reflect different ways that the service provider can choose to integrate a third party into their operation. So to talk about the first one, which is contact monitoring, this is what it looks like. Because it's a single party mode, you just have the one service provider that users interact with. And because there is nobody in the system to make sure that every change the service provider makes to the database is being done correctly, this responsibility ends up falling sort of partially on users. So whenever a user looks up a key for someone that they want to talk to, they have to remember some information about what they were shown by the server. And then in the future, on a recurring basis, they continue checking in with the server and verifying that what they were shown previously is still present. So this is how we verify that nothing is ever secretly added and then removed from the database really quickly. If the service provider maybe maliciously adds some entry to some user's account and shows that malicious entry to one of the user's contacts, then either the service provider will try to remove it at some point, in which case the contact that got shown the entry will see that it was removed and they will be upset, or it will stay in the database and the user who owns the key will eventually see that it's there and will be upset. And of course, the thing to keep in mind here is that if people are looking up a lot of random keys with this deployment mode, then they're going to have a lot of auditing to do because the auditing difficulty scales linearly with the number of keys that you look up. So that's the catch here, essentially. The second mode is third-party auditing. This is one that I think more people are familiar with. With this mode, the service provider does all the actual work of hosting and running the KT server, and it regularly checkpoints with a third-party auditor. So as part of that checkpoint, it will show the auditor all of the changes that it made to the database, and the auditor will check that the changes were done correctly, and if they were, the auditor produces a little signature basically saying like, good job, and the service provider can show that signature to its users as evidence that it's continuing to behave correctly. In the event that the service provider ever does do something malicious, for example, by trying to hide something that was previously committed, then the auditor will refuse to provide its signature. And without that signature, users will eventually stop trusting the service provider. And what you really get here is efficiency, because now users don't have to do all of this work of making sure that nothing is getting removed from the database themselves. Like I talked about in the last slide, because the auditor is doing that checking for them so they can kind of rest a little bit easier. The third mode described is third-party management. This is meant to fit a little bit more into like a software as a service pattern. So you have the manager on the right who is now doing all of the work of hosting and running the KT server. And the service provider is really just forwarding requests from the user to the manager. But importantly, because it's in the middle of this interaction, it is still able to enforce its own access control policies, and it can control when new entries are added to the database because it has to sign them. So this creates a kind of division of responsibility. So if you think about what you would do if you were trying to launch an attack, the manager can potentially construct the tree incorrectly because the manager is responsible for holding the tree and building it. But you can actually accomplish much with that without being able to sign new entries to be added to the tree. So you can like move things around, but you can't actually add any new malicious entries. On the other hand, the service provider can add a malicious entry, and it can do that without the user's permission, but it's not going to be able to later hide that from the user. So to actually succeed in adding something malicious to the database and then hiding it from the user, these two have to collude to actually succeed. And what's interesting is that you get the improved efficiency of the last deployment mode because the manager is kind of acting as an auditor. So users can know that the tree is being constructed correctly. And you also get a security benefit from the fact that this auditing is happening proactively and continuously. If some party in the system misbehaves, it's not like you find out in a day or a week or something, you find out relatively immediately. So one thing which is notably missing is anonymous third-party auditors. And I wanted to quickly address the idea that you could have anonymous third-party auditors, sort of like how certificate transparency works. With this approach, the service provider doesn't have a strict dependency on a third party. They just kind of publish an API that lets anyone that wants to perform an audit. I actually intentionally decided not to do that here because, first of all, it does imply out-of-band communication, which, like I said before, I am trying to avoid because the security that you get from it can end up being a little bit fluffy. And second, auditing endpoints tend to be very expensive because they produce a lot of outbound bandwidth. And also the fact that they produce a lot of outbound bandwidth in response to small request payloads also makes them really easy targets for abusers. So it's easier to launch a DOS attack against these endpoints and also just take advantage of the cost asymmetry of it taking the log, or of it costing the log a lot more to respond to a request than it does for you to send a request. So that is why I decided to omit this. But the idea is that between these three deployment modes, that there's always something where someone can be happy. But yeah, that is all that I have. Thank you.
Yeah, just to clarify that we're not asking in the room to accept this as an initial draft. This was just more of a existent proof that the problem is solvable, and one possible approach for this. So yeah, thank you, Brandon.
Okay, so it sounds like we didn't have that there were two of the design goals where there was disagreement, and the first was what the role of third-party auditors would be, whether it's required, not there, nice to have. And the second was to what extent, whether metadata privacy protection is sort of an extension you can add an add-on later, or whether it's something that has to happen. So modulo those two things that are being debated, do people feel generally good about the rest of these design goals? I'm going to go ahead and put up if anybody wants to jump up at the mic and ask a question, a clarifying question, or rephrase it or whatever, go ahead. But if I don't hear anything in a couple minutes, I'm just going to put it up on the poll.
Okay.
So I was
Richard,
just,
go
thanks.
ahead.
Yeah, I was just going to clarify my earlier comments about third-party auditing in light of what DKG said. I think DKG captured my comments more accurately than I did. I was presuming that there was some scheme for, by way of more or less CT-like auditing, where any third party could act as an auditor of a log, performing a standard set of computations. Not that there needed to be some designated third party trusted by all people. So I think with that flavor of third party auditing is what I was envisioning we would need here. And while I've got my mic open, I will say that I think these are probably a non-exhaustive set of design goals. We'll probably need a few more. For example, making some of the design decisions that Aisha's presentation brought up.
That's not bad, actually. It's not bad. Okay, 10 seconds.
Okay, 10 more seconds. Okay. Would the person who voted do not raise hand want to make a quick summary of their objection? Okay. Feel free to make a comment on the list, but that shows quite good interest. I think we're on the right track here. So, go ahead and ask.
All right, so obviously we need to work on the charter, and we'll do this on the mailing list. The question we would like to ask now is who's going to participate in working on the problem in the working group, if it is formed, like editing documents, commenting on the mailing list, reviewing documents. Participation in the broad sense of the word. Yeah, he's typing.
Okay, 20 more seconds. Okay. That shows some strong willingness to participate. I'm gonna close this here. Yeah, you want to go ahead and read it?
So Alicia, I think Alicia posted a comment in regards to earlier. She said that her audio wasn't working. It seems to me the critical dependency on the third-party auditing, which remains open, is a concern. So yeah, we know we need to get consensus on this point. Okay, so let's.
Okay, we're going to invite Roman at the microphone.
Hi, everyone. So first, I want to say kind of thank you for this conversation. And I want to say, actually, I think we have something very novel here. To my knowledge, this is the first time we've run a BOF where all of the proponents are remote. We have folks in the room and others participating. So I think that's great that we have energy to bring kind of new things into the IETF with a lot of different dynamics. Thank you to Brendan, Jaslyn, Antonio, and Isha for bringing this material to us, having this conversation. Really, Alexei and Rohan, thanks for grinding it and polishing it and facilitating our conversation. I think we've had a great chat here. So top line, as the chairs were saying, I think we have a strong signal to do work here. There appears to be interest around kind of KT. We have volunteers to be working on these. I think we have a sense of some of the design goals we want to hit. It's clear we got to polish a little bit more. So to me, that means kind of next steps. We're going to go to the list. We should probably create a charter which tries to be very, very, very much more concrete about some of the things we talked about, and we're going to have to iterate from there to make sure that we have it right. But the strong signal coming from this meeting is that we have interest in this, and we really should figure out a plan of how to do work for that in the IETF. So please join the mailing list if you haven't been there. And I would assume in the coming weeks, the proponents, the chairs, and I will kind of work to get you something to look at. Thank you so much for coming, and thank you for your feedback.
Thank you, everybody. Enjoy your cookies.
Yeah.